Greetings, everyone. We're up to lesson 6 now for trigonometry for students and surveyors. The last episode 5, we used some practical trigonometry. We measured a tree height, a span over a river to calculate a bridge length if they had to get one in there. Fun stuff like that. And then we just started in with the law of cosines, just so I could check my tree height, because I had 2 right triangles that made one non-right triangle, so I used the law of cosines. I used my HP 35S and entered all the numbers in there, and I was going to tell you, I told you in the end that I was going to try the same equation on the 42S, the free download for your iPhone or your Samsung, and I did try it on there and it worked just fine. So that's really good news. So that just really shows the power of that 42S, and I'll leave that for now. So the first fun thing is, it's going to kind of be aimed at surveyors, but it's trigonometry, and this is how we use it when we're surveying, and students can see how beneficial this is. So what we have here, this is my drawing of a concrete structure. This could be a catch basin. There's the same thing as it's a round. It's called a type 2 catch basin. Or the sewer manholes look basically the same thing. The bottom is different. They have a floor with a channel in them. This is a pipe. This is a storm drain. Wasn't planning on getting too much into it, but water goes through these, and this pipe should probably be up a little higher with my drawing. But the sediment, the turbidity and the sediment collects in the bottom, and over time they'll come, and you've probably seen the vacuum trucks, they'll suck all that sediment out and take it away in a toxic site and burn it, or whatever they do to purify it to get rid of it. So one of the important things that surveying needs, when we survey and we do mapping, and we go out into the street or we go somewhere, we have to get what's called measure downs. We need to know, and the engineers need to know, what this elevation is. This is called the invert. Invert of the pipe is the bottom inside of a pipe. So they need to know what that invert elevation is. So there's a lot of different ways to do it, but this is kind of an old school way where they used to use trigonometry. So we're going to kind of reintroduce that, and we're going to go from there, figure out how we're going to do it. And yes, I have it right here. Okay. So we're going to do that. So eventually they'll get an elevation right here. When you shoot it, you'll get an elevation. That'll give them an elevation, and subtract that elevation, that'll give you the invert. I don't want to go into any detail, like if they shoot someplace else, you have to adjust if the root lid's crooked. That's a little bit too much surveying right now, technical surveying, inside baseball type stuff, but we'll get to that in later episodes when we start getting into surveying part. So how do you do that? If you walk up here, you have a rod. A rod is basically, it's a fiberglass rod that telescopes in sections. We use those. We can take the top few out and use the bottom, and you read it with a level that only shoots flat. I'm going to say 0 or 90 degrees, and then you can read the rod. You've probably seen people on the road doing that, and just taking, that's called differential levels. The other way is to turn it around, have all your pieces in, and go up. And then you measure backwards from the prism that's up there back down, and that's called topo. And you shoot that prism with your gun, with your transit gun, theodolite, total station, multi-station. You shoot that, you enter in the rod height, it'll subtract the length of that rod and give you the elevation at the bottom of the rod, whether it's the ground or whether it's that, the top of that. So we want to get this invert elevation from here to the lid. Let me draw that in. This is what they're really looking for. Is this elevation here. And not this elevation, this length. So they can subtract whatever this elevation is to get to that. We'll just go put our arrows in here. Okay, so you shoot this, or shoot it eventually. To get this, it's just a simple trig problem. Now, you remember when I talked about the 3, 4, 5 triangle, how it would be a very handy reference tool, a template, a virtual template to have, because we've done so much 3, 4, 5 triangles, you're probably very familiar with what should be. So if you look at something like this, this is, now this isn't a 3, 4, 5 dimension, it's not the same quite dimensions, but we're going to pretend that this is side 3, this is side 4, and this is side 5. We're just going to pretend that. So the idea on something like this is you got to be able to identify, you got to be able to use what information you have and be able to identify which one of these symbols do you use, sine, cosine, or tangent. Which one of these functions, sine, cosine, or tangent. So you get your rod in there, and you put the bottom of the rod in the invert, and you angle it up till it hits the top of the rim. Because that's where it's going to be shot eventually. Somewhere here it's going to have that elevation, so those will have to match. Those two elevations are going to have to match. So what are you're looking at, put the rod in there and you can measure the rod right there. You can read the rod. Okay, I guess 14.75. We're going to go with tenths on this one. Engineers, 14.75 from there to there. So what is this one? Well, now you got to figure out, I can't stand there. Now you have to figure out which function to use. Okay, so what we have here, we're looking at here. I'm just kind of hesitating because I want to give you guys a little bit of time. So what we're looking at here, there's sine, cosine, or tangent. Now we have this. We don't have that. So we can't use. Well, let's just go through what we have to use. We have that. So we have this diameter. Now this is where this came from. 6 foot. That's the inside diameter of this concrete structure. The walls are somewhere around 3 inches or 4 inches thick. I'm not sure, I can't remember. Most of these structures are 4 feet in diameter. Some of them are bigger, they're 6 feet, and some of them are bigger yet. But for our sake, we're going to have a 6 foot inside diameter, and we're going to have a 14.75. So now we've got a figure here. And our angles here. So we have a 6 foot. We have a cosine. We have a cosine because they connect right here. So we have the adjacent over the hypotenuse. So that's what we're going to do with that. We have the adjacent. So you grab your calculator. And the adjacent is 6 foot. So 6 divided by, or 6 enter. 14.75, or divide by 14.75 is 0.4068. Now we're going to multiply that. Now we want the arc cosine of that. Arc cosine is 65. It's basically 66 degrees. 65, 99, 73. And that is 65. 99.73. That's that angle, and then we're going to store that as 7. We're going to convert that. 65.59.50 is the arc. 65.59.50. All right. So we're going to recall that angle, 65.9973. Now we can either figure it out through the cosine or the, the tangent. Let's go with tangent. So we're going to go tangent, and we're going to go 6 times 13.4745. And that's this length here. So that's how you do that. That's one way to do it. I'm trying to think. Sometimes I get confused when things are not the right angle. I would probably draw that if I was having any trouble, draw that sideways and do it the normal way. That would also be the sine. You could go with the sine on that. Let's recall that angle. And we're going to go sine 0.91, 14.75 times 13.475. So you can do that through the sine or the cosine. Remember, the sine is the opposite over the hypotenuse from this angle. So that's how you do that. So we'll move on from that. I was going to draw a door. These are some of the things. This is some of the things we used to do all the time. Yeah, I guess we'll just leave that now. What I want to show you is this thing right here. This is just a little kind of an afterthought I put in here. I made gates this summer. I had to make new gates for my house, so I had to figure out. Here's your gate, and then you got all your boards in there, so on and so forth. Hinges. Now I wanted this. I had a dimension here and here. It's really easy. It's a rectangle. But if that is not square, you can have the right dimensions. They're going to be the same. Let's say 4 feet, 4 feet, and 6.5 feet. That's going to stay the same. Even if you twist this, it's going to be a parallel. It'll become, instead of a rectangle, it'll be a parallelogram. Well, you don't want that. So what you want to do is 4 and 6, and you want to calculate that hypotenuse, and then put a brace in there, and put a brace in this way. Now it depends on your wood. You can put the brace, right in the corner, or you can put the brace in the corner that way and that way. Anyways, doesn't matter. I'm not a good drawer. Make sure you put the brace in from the bottom up. Now some people they'll say, yeah, we need a brace in there, we need that diagonal. People put the diagonals in there. But they'll put it in, so this is the hinge side, they'll put it in up, slanting up like that. Well, just think of this can hinge, it's not holding anything. But if you have the brace from here down to here, so they're not gonna be able to push down. That's just gonna push that into there. But if you have the brace over there, everything can just kind of collapse. So there's that. So that's one of the things I did. I made a shed, a shed on my shed, a little shed hood for my tool shed. We got a storage shed out there, and I made a shed for all the shovels and rakes and things like that. And I just used trigonometry to figure out how high I wanted up, how far I wanted over there, just figure out what angle I wanted, and then after that I had a brace going out at 90 degrees. Add that to 90, subtract from 180, then I found my third angle, come and cut everything up, took it back out, and nailed it or screwed it back in, nailed it in. So it saves a lot like I used to do, saves a lot of work like I used to do. Another thing, I do a lot of stuff. I built all my furniture, or not all my furniture, but I built a lot of my furniture. I use it quite often when I'm doing that. It's easier to draw stuff out and calculate stuff out. This here, I'll show you what this is all about. Simple little thing here. First of all, this is a scale. That's 25-degree angle. This is a scale, and this scale just came from a 1 in 30. It came from here. And so I measured. Now here's what I measured. Here's what I'm talking about. This is a hand plane. I have it kind of disassembled right now. This thing screws on to the blade. I have the blade off because that's what I want to show you. This is a hand plane for planing wood, and you really want to get that sharp, super sharp, cut a little thin. If you get it sharp enough, it just pulls easy, pushes easy. You get very thin, almost transparent shavings, just beautiful. If you get a dull one, you're working, it's jamming. So you want to be able to sharpen these. Now, what they're calling for is a 25-degree angle. So if you're just holding the blade and trying to get an angle, there's a good chance that you're not going to be able to, every stroke that you're going, it's going to move a little bit. So they made these little devices here. What is it called? It's just called a chisel guide. And then it screws on here. So, but you got to put it on here at the right length to get, because they're calling for a 25-degree angle. This angle should be 25 degrees. Yeah, it looks like it is. Okay. So how do I get that? So you can slide this, unscrews, and you can slide this wherever you want it, and then tighten it back up. And then, usually I'll use like a piece of really fine 1000 grit, 3000 grit sandpaper on top of a super hard surface, maybe a plate of glass. And then it's much easier to work than this little stone. This is just for demonstration purposes. So how did I get that? Well, it's a triangle. And what I had was, this, of course, this is scale. I measured from the bottom of the roller to where the bottom of this little roller here to where that fits in there. And I roughed it in a little bit, but it came out to 40 on the 30 scale on that plastic scale. So then I just did 25. Let's go where are we at here. So we're going to go 25. Now we don't have to convert because it's a degree. 25 degree, and we want the sine. We want this distance here, that's the sine. We want the opposite over the hypotenuse. We have the degree, we have the opposite, we're looking for the hypotenuse. If we were looking for the tangent, now this doesn't need to be here. If we were looking for the tangent, then we would select tangent. But we want the hypotenuse. So 25, we want sine. And then we want, so it's 0.4226, and we want 40 times, and it's 16, oh, wait a minute, hold on, baby. All right, 25, enter, tangent, or sine, and we want to, oh, sine, that's right, I didn't inverse it to 1x, because the hypotenuse is always longer, so let's just go 1x, and now 40 times, and now we have 94.64. So on that same scale, I just measured out. So I'm on the 30 scale. I measured 94, roughly 94.64, centered it over there, mounted it down, and as you can see, I got my 25 degrees. It seems like it's perfect. Okay. There's that one. Okay. Mainly what I'm showing you here is that there's so many practical uses around the house. If you have a wood shop, if you have crafts, construction, you know, house pitches, those are rise over run. Those are like a 412 pitch, a 612 pitch. That's all that is. If you're making a wheelchair, we'll go through some of this stuff. Maybe a wheelchair ramp. ADA, American Disabilities Act, will require a certain slope. I'm not sure what it is. It might be around 2%, maybe a little bit more. But if you have a certain height, and you have a certain height, and you have to have a certain slope, then you can calculate how long your ramp needs to be. It might even have to have a turn in it, or a platform where you go, you know, so far one way, a platform and the other way. But you got to have so much length to get that height at such and such a percent. So knowing trigonometry makes it real simple to do. That is good. I'm going to go one more little quick thing here on my eraser. Okay. Let me do this. Well, I won't do that. I'll do this. This is just so I can get quite a few things into today. This is a good lesson too for teachers if you're trying to teach and you have students who think, yeah, I don't need this stuff. Because that was me. That's me and a lot of people I know. Don't need this stuff. When I was in grade school and I was in high school, I just kept looking out the window and said, I want to be out there, man. I want to be out in the, I want to be outside. I want to be out playing. I want to be out in the mountains. When I got older, I wanted to be in the mountains. Eventually I did. But anyways, when I did get to the mountains, we lived in a remote area. My wife and my family raised them up there. I ended up building log homes. Actually, that's the house behind here. We built log homes for ourselves, for other people. I milled lumber for mining crews, for other people. I milled with an Alaskan chainsaw mill. And I got to where I was doing a lot of it. And I would get a tree, and it's called making a cant. I would get a tree and I would set my mill. You have a track up here, like this. It kind of comes over like that. And then your mill sits on here and you adjust the bar like that. And then you take your first cut there. Then you can either flip it, or I use a mini mill and cut this one, and so on and so forth. Well, what I was finding is I was just guessing on this first cut. And sometimes I would end up having too much, it's called wane, it's bark on the edge of the tree. I'd have a little too much of that, so the board wasn't quite as useful as I wanted it to be. Or I'd cut too deep, and I would not have any, and I'd have taken some of that good wood would be left on the slab. So I started scratching my head trying to figure out how to convert those over, or how to find the ratio of what that is. And I'm sure a lot of people are watching saying, well, that's pretty simple. Well, it wasn't for me. So the reason I'm telling you this is that through this process, I learned to appreciate geometry and trigonometry. What it is you have the diameter. Let's just say you have the diameter. I could have always done this, just crossed it and measured across. That's one way. I didn't ever think of that. But I tried different things. I don't know, it's been too long ago. It's been over 30 years ago, 35 years ago when I did that. But when I found out that this is the diagonal, it's a 45 degree. This is a 45 degree angle, triangle. Whatever the height. So this is 1:1 ratio. It's 100%. This would be 100% slope, and this is what you have here. So this would represent the diameter in the tree, and this would represent these sides that I was looking for. Well, it just turned out, as I experimented and played around, that dimension is 1.414, and what that is, that's the square root of 2. If you hit 2 squared, it's 1.414, and so on and so forth. So then I could take a diameter of the tree, once I figured that out, divide it by 1.414, and find out where this first cut is. I'd make a mark, I'd make a pencil mark. Then I'd set my mill to come right down to that. That would be my first cut. And I started salvaging a lot more, or optimizing the tree a lot better on there. So that was pretty nice. Now that was another thing that I did that I thought, well, that's pretty cool. Here I am way up in the bush in northern British Columbia with my family, and I'm out here milling lumber. And I had a good use for math. It came in very handy. So the square root of 2 is 1.414, and that represents the hypotenuse of a right triangle. Kind of handy to know. All right. And you never know. So don't say, like I say, I went and lived my dream in the woods, but I still needed math. So students that are watching this, teachers who are teaching this, you got to impress on people that they don't know whether they're going to need this stuff or not. They most likely will at some point. So there you go. All right, now there's other things that trigonometry is kind of fun to do. You've probably heard, if you have anything to do with shooting or know anybody that likes to shoot guns. Let me get this out here. And we'll just say paper targets, long range shooting, paper target shooting. There's a term they use, it's called minute of angle. When people sell a gun, or the gun seller sells, they say this shoots minute of angle, or it shoots sub-minute of angle. So what does that mean? What's minute of angle mean? Well, first of all, because it's a degree, it's going to spread out. The farther you go, the wider that's going to be. It's like on a protractor. The smaller your protractor is, the tighter those degrees are to each other. If your protractor was real big, you'd have a little bit bigger and a little bit bigger and a little bit bigger. So as far as you went out 300 yards, 500 yards, the degrees are going to be a lot bigger. So minute of angle is a measurement of, it's going to be like, the farther you go, your bullet spread still might be a lot larger than it is here, but it could still be minute of angle. Okay, so minute of angle, the rule of thumb is 1 inches, and that's, if you have a bullet spread like this, this, and this, let's go like this. You spread from center to center. They measure it from outside to outside, and then they subtract the diameter of the bullet. If you subtract the diameter of the bullet, half the diameter, it puts you in there, half the diameter puts you in there. These are people who are competition shooters and they use calipers. I'm just trying to demonstrate how you do it. So that's how you measure, and that shows your spread. And they're trying to figure out, they're trying to get their guns to shoot really, really accurate. They shoot 1,000 yards now or more. They shoot way farther than that now. It's incredible. So the rule of thumb is 1 inch at 100 yards, 2 inches at 200 yards, 5.23 inches at 500 yards, 10.472 at 1,000 yards. 10 inches at 1,000 yards is a 1 minute of angle group. It is actually a 308, which is a very popular round, drops 300 inches or around, now these are plus minus, depends on a lot of things. Around 25 feet at 1,000 yards, a 300 Win Mag, 250 inches plus or minus 20 feet. They have other rounds that, you know, other the calibers, heavier calibers, different ballistic coefficients on these newer elongated bullets that do better than that, but not that much. That's a long ways to try to and hit something, plus wind edge elevation, so on and so forth. But rather than just go by the rule of thumb, a shooter might want to know exactly how to do this. So let's just look at this. So you have 1 minute of angle. That's the written, the HMS, hours, minutes, second. 1 minute of angle. You convert it to HR. You guys know how to do that in your calculators by now. That's 0.167. Now when you get that, this might surprise you. You can use either tangent or sine. And why is that? Well, it's because the triangle you have, you can look at that yourself. If you go 0.167, it's because your triangle, that's your angle, is almost 2 parallel lines, but they're not quite. And what this, and I lost my light again. We're probably okay. That's happened before. So that's why it doesn't really matter. You're looking at a tangent here or a sine here. So you can use tangent or sine it when you're that tight. We'll talk about later when you get a bigger spread than that. So 1 minute, you convert it to HR, which is 0.167. So you already got your angle, you convert it to that, and then you multiply it times the hit the tangent or the sine, 1.047. Let me work that out. All right. So we're going to go 0.01, and now we're going to convert it, and that comes to 0.167. Okay, now we want the tangent of that. We'll go tangent. That's 0.0003. I guess I didn't write that down. And then we want 3,600, and so that's 3,600 inches. So 3600 times 1047. 1047.2